All right, let's talk about something that's literally all around you, but completely invisible. We're diving into the tech that builds the heart of almost every gadget you own. It's a process that happens on a scale that's almost impossible to wrap your head around. But its impact? Oh, it's absolutely massive.
I mean, really think about it. The screen you're looking at right now, the tiny processor chugging away inside your computer, they're all made of these incredibly complex, layered materials. So how in the world do you build something that's only a few atoms thick? Well, the answer is this amazing technique that's been quietly changing our world for decades.
Okay, so let's get right into it. What is this stuff? It's called chemical vapor deposition, or CVD for short. And you can think of it as the ultimate art of building things with pinpoint, atomic-level precision.
You know, the easiest way to picture CVD is like atomic-level spray painting. Seriously. But instead of paint, you're using these special reactive gases. And instead of just coloring a surface, you're actually growing a brand new, super thin solid layer right on top of it, one atom at a time.
And the basic process itself, it's actually pretty straightforward, conceptually at least. First, you introduce these carefully chosen gases, we call them precursors, into a chamber. Step 2, you heat up the surface you want to coat, that's the substrate. Now that heat is the trigger for step 3, a chemical reaction, and boom, the result of that reaction is that a solid, thin film starts to grow on the substrate. It's like construction, but on a microscopic scale.
So where did CVD really become a superstar? Well, it was in building the silicon chips that are the brains inside, well, everything. All of our modern electronics owe a huge debt to this process.
And in the world of semiconductors, it all comes down to one word: control. The electrical properties of these thin films, everything that makes them work, is decided by the conditions inside that reaction chamber. We're talking about super precise temperatures, the exact mix of gases, even the angle of the substrate. You get it just right, you've created a perfect material. But if you're even slightly off, it's completely useless.
And this precision is absolutely everything. Just tiny tweaks can lead to these massive differences. For example, if you deposit indium tin oxide at exactly 1100 degrees Celsius, you get this perfect film for transparent electronics, like your phone screen. Or, by just fine-tuning the percentage of something called yttria in a ceramic film, you can suddenly boost fuel cell performance like crazy. It turns out every material has its own secret recipe for perfection.
But here's the cool thing. CVD isn't just about building the brains of our tech. It's also about building its armor. It's used to make everyday things tougher, stronger, and way more resilient than they could ever be on their own.
Right. This is where CVD becomes a tool for making materials that can survive in the most extreme environments. We're talking about coatings on jet engine blades that laugh at incredible heat, or on medical implants that have to last for decades inside a human body. These aren't just thin layers, they're high-performance functional shields.
I mean, just look at the versatility here. It's wild. Need something unbelievably hard for a cutting tool? Bam, titanium nitride coating. Need a super low-friction, wear-resistant surface for engine parts? Diamond-like carbon is your go-to. What about a coating for a hip implant that your body won't reject? You can literally deposit a layer of biocompatible hydroxyapatite. There's a custom-designed coating for pretty much any problem you can think of.
But you know, a great coating isn't just about the material itself. It's only as good as its bond, that interface, with the surface it's protecting. A ton of new research is focused just on this. For instance, studies have found that if you pre-treat a surface with something called ion etching before you put down a diamond-like carbon film, its sticking power and performance go through the roof. The foundation matters just as much as the armor on top of it.
Okay, now this is where things get really mind-blowing. We've been talking about thin films, but scientists are now using CVD to create revolutionary materials that are, and this is hard to believe, only a single atom thick.
So welcome to the next frontier. We're talking about materials like graphene, which is just a single sheet of carbon atoms, and this whole other class of materials called TMDCs. These things have bizarre, wonderful properties that could unlock brand new technologies we can barely dream of, from super efficient electronics to all sorts of new sensors. Check out this number, 91.5%. So what does that mean? Well, that is the corrosion-blocking efficiency that scientists got by coating a piece of copper with a single layer of nitrogen-doped graphene. Let me say that again. A layer you cannot even see provides over 90% protection from rust. That's just an incredible demonstration of what these 2D materials can do. But, as you can probably guess, trying to grow a perfect, unbroken sheet of material that's only one atom thick is phenomenally difficult.
Remember that process control we talked about for semiconductors? Well, for 2D materials, you have to dial it up to 11. It is an incredibly delicate balancing act.
So let's take one of those TMDCs, molybdenum disulfide. Researchers found there's this super narrow temperature window between about 820 and 900 Kelvin where it grows into a beautiful, flat, perfect 2D film. But if you go just a little bit hotter, the atoms start stacking up on top of each other and you lose all those amazing 2D properties. You just end up with a useless, bulky 3D crystal. That's how fine the line is between a breakthrough and a failure.
And the innovation here just keeps going. It doesn't stop with flat films. Scientists are using CVD in some unbelievably creative ways. They're growing carbon nanotubes right onto fabrics to make them stronger. They're using waste biogas from palm oil as a cheap source to grow top-quality graphene. They're even creating these nanodiamond coatings for battery electrodes to make them safer and way more efficient. The possibilities are just exploding.
So, after all that, from the chip in your phone to invisible armor to the batteries of the future, what's the big picture here? What's the main takeaway?
Well, here's what you really need to remember. First, CVD isn't just one single thing. It's this huge, versatile toolbox for building materials from the atoms up. Second, control is king. Tiny adjustments to the recipe can unlock completely new properties. And finally, you have to realize that CVD is the foundation for the technology we use today, and it's the bridge that's taking us to the incredible innovations of tomorrow.
And all of this leaves us with a really fascinating question. We've managed to develop a technology that gives us this almost godlike control over matter at the tiniest scales imaginable. So now the only real limit is our own imagination. What should we build next?